Oh. Coffee doesn't do me any good back here. I'll begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class, these students. Just ask you to encourage them to persevere and just keep doing what they're doing, to understand more. Help us to glorify you. What we do this day, help us to understand a little bit more about calculus, Lord. In my prayer, Lord Jesus. Amen. So this example, bequeathed to me by the previous instructor here, find the area of the region bounded by y equals 9 over x and y equals 10 minus x. So this here is the next top. This is what we're doing next week, among other things. Like next week we're going to talk about how to calculate the area bounded by curves and also like how to calculate volume of, solids that are reasonably simple. And so what he does here is, first of all, makes a graph, right? So the reciprocal function, 9 over x, is this guy, and the 10 minus x is that guy, all right? He looks for intersection points. That shows how to graph it, right? He puts these two, y equals y, that's where they intersect. It gives you this lovely quadratic equation, so either 1 or 9 are the points of intersection. And then he says that a is equal to this. Now let me explain why that is. So what you can do is you can chop this up into a bunch of little rectangles, like so, right? And the little infinitesimal area of that rectangle is equal to 10 minus x from the top minus 9 over x from the bottom. See that? The height of the rectangle is the difference of the y's, and the width is dx. You can make such an infinitesimal rectangle for each x between 1 and 9. So to add them up, we integrate. Integration is a continuous sum. We integrate the dA from 1 to 9. You do the integration, you work out to 20.22. So that's the area that's between those curves. See, that's something we haven't done in here yet. We talked about the area between, between a curve and the x-axis, but we haven't done an example with area between two curves. Now this one over here is more exciting because he's asking what's the area between these two sideways parabolas. So like x equals to 8 minus y squared and x equals to y squared plus 2y minus 4. These are parabolas which open left and right respectively. And here's a picture of them. And so like the difference of the right one, so this is, and when we talk about it next week, I'll say that this is like the right x minus the left x. That gives you the width of the approximating rectangle. So like the approximating rectangle here would look like this. So dA would be like the right x minus the left x. What's the thickness of the rectangle? Now instead of dx, it's dy. Right? dy is the thickness. So it turns out that these points of intersection, if you put these two things equal, it gives you y equals minus 3 or y equals 2. So you have such a horizontal strip all the way from minus 3 all the way up to 2. You integrate the dA by integrating over y, and that calculates the area between those two parabolas if we were to finish it. So, yeah. So thanks to the previous instructor for leaving this up, because I think it's good for us to see somebody else's work on occasion, and there it is. And for those of you who can't see this because like it's too low relative to student heads and such, you're not missing anything. It's just, what is that? He's just used the letter Y instead of X. Well, I'm not sure what that is. Yeah, anyway. All right, so let me erase the board here. You guys have any questions now that I've... 327. 327.
I feel like I should know this, but I'm not going to lie. I do not.
See if I can find my problem sheet here. But these two examples, it's pretty indicative of like what we'll do with integration. Integration just allows us to add up. things. So anytime we want to sum things, integration's your tool. Now, let's see if I can find my sheet. Well, this is not it. Well, just a second. I've got it on the computer. I just need to get it out. Oh, I seem to have forgot my attendance sheet today too. I'll top hat for you guys. And then we'll feel better about our day, right? Come on, computer, wake up. You did say 327, right? Okay. All right, let's get out of here. Where are we? Top of the hat to you. Where did it go? Wonder how much time you guys waste in your education top hatting. What percentage? Is it like 2%? Like of the time in classes, like what percentage of time do you waste on top hat? Maybe 1%?
I think that probably adds up to like several hours.
1%, but it feels like 10%? No. Let's see here. Your top hat code for today will be 5012. Let's see here. We're in mission 9, right? Come on. Show yourself mission 9. All right, there we go. Whoa. Okay, 320, 327? Oh, okay. Good question. So you want to know how to integrate like tangent squared. Let's see here. So example 1, suppose we're going to integrate tangent squared of, let's make it weird, alpha x dx. There we go. So what do you guys have any ideas?
So what do you start off with making a sine squared? What's that thing called? You said alpha.
Alpha, yeah.
Sine squared alpha x over cosine squared alpha x.
Ooh, I wouldn't recommend it.
Would that be one route?
Yeah, I don't think that's what you. I think what you want to do here is like, so we know that tangent squared theta plus 1 is equal to secant squared theta. And we like secant squared theta. That's an elementary integral. So we want to go that direction. See, I like your idea of converting to sine and cosine, but the trouble is that it's an even number of sines and cosines, which doesn't work out nice. Like you have to have like an odd total number of sines and cosines for those to work out nice and pretty. Okay, so tangent squared is what? Secant squared theta minus 1, right? So this is the integral of secant squared alpha x minus 1 dx. Now what should I do? Let u equal what? Yeah, you might be able to just integrate, admittedly. Like I've been skipping writing this work down, but let me write it down. Just let u equal alpha x. Yeah. If u is alpha x, then du is alpha dx, or dx is du over alpha. So we have, integral of what? Secant squared u minus 1 times du over alpha. And that we can just integrate. Yeah? So what we got here? We got 1 over alpha parentheses, the integral of secant is tangent. Secant squared is tangent. So tangent of u, integral of 1, well, minus 1 is just minus u, plus a constant. So that is 1 over alpha times the tangent of alpha x minus alpha x plus a constant. Or if you like, you could write that as 1 over alpha tangent of alpha x minus x plus a constant. Whether or not you want to leave the alpha factored out, it's up to you. So that should pretty much show you how to do 327, right? Yeah.
Not to add first, but I'm not gonna lie, I confused myself a little bit. We went over the class so many times.
Not really. I mean, we touched on this briefly, but
What's getting the sequence where whatever it is, that's what you would work from there.
oh yeah. Other questions? Yeah. 338. Oh, wonderful question. So we need to talk about this. Let f be even function with domain symmetric about origin. So what I'm trying to say is, like, basically, you know, something like minus c to c is a subset of the domain of f. All right. I want to suppose that f is continuous there. And I want to talk to you guys about how would we integrate, say, from minus a to a, or let's say minus b to b, minus b to b, f of x dx. How would we understand? I mean, there's a trick here that I can teach you guys. This is a very useful labor-saving device. One of the things you may have noticed is that integrals from 0 to a number tend to be really nice in terms of computation. Integrals from minus a number to a number, they're not bad, but they're not as simple as integral from 0 to something, right? So there's the nice, if we can rewrite this as an integral from 0 to something, that would be nice. So let's work on that. So first of all, this is the integral from minus b to 0 of f of x dx, plus the integral from 0 to b of f of x dx. First of all, that's just like a basic property of the integral, right? Let me draw a picture of what's going on here. So if f is even, what's it look like? If this is the graph, right? What does the other half of the graph look like? I regret my picture. So, I mean, f of minus x is equal to f of x is the thing, right? So by just geometric, you know, you could argue geometrically that if I go from, you know, 0 to b versus, you know, 0 to minus b, that this area should be the same as the soon-to-be green area, right? Because even function has this symmetry. Let's work it out, though. Let's work it out with a u substitution. What substitution can I make here? So what I'm going to do is I'm going to let u equal to minus x. If I do that, then u of minus b is equal to minus minus b, and u of 0 is equal to 0. So this becomes the integral from b to 0 of f of minus u times minus du plus the integral from 0 to b of f of x dx. But notice that, yeah.
What would we do if it's an odd function?
Oh, we'll get there. So, very good, but give me a second. So, that is a very good question. That's the next thing. Very next thing I'm about to say. So, what is f of minus u? Even, so it eats the minus, right? So you've got, this is just, f of u times minus du. So pull that minus out here and flip the bounds, right? When we flip the bounds, it gets us a minus. So this is literally equal to the integral from 0 to b, f of u du, plus the integral from 0 to b of f of x dx. But these are exactly the same quantity. See, whether I use u for the integration variable or I use x for the integration variable, either way it's a quote-unquote dummy variable of integration. So in short, I get 2 times the integral from 0 to b of f of x dx, right? So this is a theorem. Anytime you have an even function integrated about a symmetric interval of the origin, we can simply double the integral over the positives. Now, you could just as well double the integral over the negatives, right? You could do twice the integral from minus b to 0. For some reason, that was more convenient to you. Now, you're asking me, Mia, what if the function's odd, right? How would this argument change if the function was odd? So we can go through the same exact argument if f is odd. And we'd have, integral from b to 0 of f of minus u times minus du plus the integral from 0 to b of f of x dx. Suppose f odd. What does it mean if f is odd? F of minus x is minus f of x, right? That's what an odd function does. So you see that step? The step right here, from here to here, is different for an odd function. Instead of the odd function eating the minus, it spits it out. The odd function spits the minus out. It doesn't just absorb it like the even function does. So that minus cancels this minus, and we just get, flipping the bounds, minus the integral from 0 to b of f of u du plus the integral from 0 to b. And what happens then? We get the same thing, but opposite signs. We get 0. So this is really nice. The integral of an odd function about a symmetric interval of the origin has to be 0. For example, if we integrate minus pi to pi sine x dx, I can tell you that's 0 without even calculating. On the other hand, I can tell you the integral from minus pi to pi of cosine x dx is actually just twice the integral from 0 to pi of cosine x dx. How do I know this? I know both of these claims are true because I know that sine is odd, whereas cosine is even. So if I integrate sine symmetrically about the origin, it integrates to 0. If I integrate cosine symmetrically about the origin, I can just double the integral from 0 to pi. Now that homework problem you asked me about is just basically about knowing this and using it. See, because that homework, so like, for instance, here's a silly, I don't know if this is really, it's more of a theorem than an example over here, but I'll call it example 3, 2, whatever, 2, example 2. This was example 2, and I suppose this is example 3. There we go. I feel like I've done more with my day if I get more examples. And example 4. So assume f even and g odd. And let's suppose that the integral from 0 to 3 of f of x dx is 21. Then we could ask, what's the integral from minus 3 to 3 of like Whew. X to the 17th, f of x, plus g of x, plus f of x dx. Here's a silly problem. I think it's probably easier, probably harder than your homework, right? This is harder than the homework problem, I think. Is that fair? Yeah, that's probably fair. Have you guys ever thought about this? How do you decide whether functions are even or odd? I mean, we do talk about it some in pre-calculus. At least I do. I try to. But there, the discussion of even and odd sometimes seems a little forced. Here, all of a sudden, the stakes have raised, right? Because if it's odd, it integrates to 0 when you've got this kind of integration domain, right? Region. So that's super nice. Can you tell me what's x to the 17 times f of x? Is that even or odd function? How do we decide? Yeah?
Guessing it's odd.
You're guessing it's odd, yeah. Because otherwise the problem's unsolvable, right? So by process of logical necessity, it must be odd. Very good. But how about this? If I let h of x equal x to the 17th times f of x, make that your function. Think about that. If I feed it minus x, what happens? I get minus x to the 17th power times f of minus x. Now, what is f of minus x? F we assumed is even. So that's just f of x. But what's minus x to the 17th is just minus x to the 17th. Sorry, English lets us down. But as you can see, that's minus h of x. Therefore, h is odd, which says that the integral of x to the 17 times f of x is 0. This makes a really nice, low computational burden conceptual question for test 4, right? If you guys understand this, there's like a question I can ask which is very simple to answer but doesn't really require calculation much to speak of. Now, on the other hand, let's see here. What did we just say? G was odd. So again, by the example 3, this integrates to 0. And this gives us, so we're just left with the integral from minus 3 to 3 of f of x dx. But then by example 2, that's 2 times the integral from 0 to 3 f of x dx, which gives us 2 times 21, which of course is 42. There you go. I gave a complex test last semester. Last semester. I gave a complex variables test. I think I told you guys about this. I had 5 answers work out to 42 in like a row. In different circuitous ways. And then the final question on the test was, how old do you think my wife is? Nothing ventured, nothing gained, you know? Let's see here. Sometimes comedy's dangerous. Oh, man. Do you guys have another question? Oh, let me talk about, one sec. Problem 329, I didn't assign it, but problem 329 has a typo. Problem 329 is supposed to read 1 plus natural log of 2 times 2 to the x dx over 3 plus x plus 2 to the x. In the problem that's posted in the homework, I am missing this little factor, natural log of 2. Without that log of 2 there, I do not know how to solve this problem. With the natural log of 2 there, you just let u equal to 3 plus x plus 2 to the x. And then this just becomes the integral of du over u, which is natural log absolute value of u plus a constant, which is natural log the absolute value of 3 plus x plus 2 to the x plus a constant. So this problem, 329, it's not bad with the typo fixed, but without the typo fixed, like, yeah, no. It's bad. It's real bad. Anyway, you guys had another question? Maybe you guys have the same question. Which one is it? Excuse me, guys. I'm sorry. 335? Yeah. Oh, yeah, we haven't done many like this. So, all right, so like, I'll change it up ever so slightly. I don't know. Natural log of 3, natural log of 7, and let me I'm trying to think of how to mess it up a little bit. Yeah, I'll mess it up. Well, fine, I'll just do it. I guess it doesn't hurt for me to do one of them. E to the x dx. I changed the bounds, didn't I? So that's something. But I'm almost going to show you how to do this one. So this is essentially problem 335. I assigned you a bunch of them. What's the harm? You'll still learn. So this one, the key thing to think about here, the thing that this is like, and maybe you don't see it offhand, but du over the square root of 1 minus u squared. See, that is inverse sine of u plus a constant. That is one of our basic integrals. So anytime you see a square root of a difference of squares at this point, you got to think inverse sine. Next semester, you think trig substitution. All right? But we're not there yet. So, I mean, what is trig substitution? It's just words, right? Just words. So how about this? We let u equal e to the x. Then u squared is e to the x squared, also known as e to the 2x, you see. And so u of natural log of 7 is e to the log 7, which is 7. U of log 3 is e to the log 3, also known as 3. So we change the bounds to 3 to 7, and then you got yourself a du over the square root of 1 minus u squared. See, du is e to the x dx, right? So this is the substitution details there. And once you have that, you're like, oh, inverse sine, yay. So it's not too bad. But if you didn't know about inverse sine, it's bad. It's like pretty much impossible. Thought I had it off the bounce. Oh well. So we've got inverse sine of 7 minus inverse sine of 3, and there you go. That would be the answer if the bounds were with that. I guess the bounds are different in the problem, right? I got 3 and 4, so I think if you change the 4 to a 7, I've solved your problem, right? But the larger point is, do you see like as you look through these problems, anytime you see like a square root of a difference, probably it's based on like an inverse sine kind of identification. What was the next question? Was that your question? Jordan? Whew.
330.
Ah, 330. Yeah, that's an interesting one. Let's look at that. So there we've got integral of x squared over x plus 1, right? That's problem 330. I'm gonna take your problem and solve a more difficult one. So we'll solve the integral of x cubed over x plus 1 dx. See if we can do that. Because if we can do that, we can do the other one. All right? The technique you want to use here is long division. So long division. Can you guys see this, or am I below the event horizon there? Is better? Okay. So we're x cubed, and we're dividing x plus 1 into it, yeah? So I start out with a x squared. That gives me x cubed plus x squared, subtract, minus x squared. So I do minus x. That brings down minus x squared, minus x, subtract. That gives me an x. So I do plus a 1. That brings down x plus 1. My remainder is minus 1. So therefore, this is equal to the integral of x squared minus x plus 1 minus 1 over x plus 1. And once you got that, then we can integrate. No problem, right? I'll finish it here. So this is, 1/3 x cubed minus 1/2 x squared plus x. And when we integrate 1 over x plus 1, what's that give us? That's right. So we get minus the natural log, the absolute value of x plus 1. Now, admittedly, this I'm making a u equals x plus 1 substitution. So du is equal to dx. So we didn't have any kind of extra factors there, you know.
Sometimes I just be confused, because sometimes when it's a fraction, we can't use u substitution from the get-go.
Well, you could have used u substitution from the get-go here to avoid the long division, for sure. That's an alternative way to do this for true. I mean, for true, listen to me. So if I let u equal to x plus 1, then x is equal to, well, u minus 1, isn't it? So the integral, I could go directly to, u minus 1 cubed divided by, well, u du, which is the integral of u cubed minus 3u squared plus 3u plus minus 1 divided by u, also known as the integral du of u squared minus 3u plus 3 minus 1 over u plus a constant, du, which would integrate to 1/3 u cubed minus 3 halves u squared plus 3u minus the natural log, the absolute value of u plus a constant. And I've run out of board space, but if we put back in x plus 1, that gives us a kind of, it's the same integral, it just looks different. I'd have to it might not be immediately obvious, but if you foiled it out, you could see it's actually the same answer. It's pretty obvious on the natural log term that we've got the same answer, right? Now, these don't have to be identically the same answer, guys. Like, this could be C2 and this could be C1. They don't have to be literally the same answer, but they do have to differ by a constant if they're both legitimate antiderivatives, because two functions which have the same derivative, they have to have the same derivative because they both have to differentiate, give us back the integrand, but they don't have to be equal because they can differ by a shift. But if you think about foiling this out, you see you've got the 1/3 x cubed, right? And if you think about foiling this out, you've got like a 3x squared term in it over 3. So there's an x squared here minus 3 halves x squared there. What's 1 minus 3 halves is minus a half, which is here. Minus a half on the x squared term. So you can work it out. They match up. Modulo the constant term, because there is a constant here overall, I believe. Like there's a 1/3 minus 3 halves plus 3 here. So C1 and C2 are not equal. They really are different constants. So yeah, if you don't know long division, this is another way around it. But you guys should learn long division if you don't know it. It's something you ought to know. Yeah? Hey, yeah? 360? Uh-oh. Oh, yes, this one. So you need to use the identity we had yesterday, right? Which one was that? You guys will have to help me out. I don't want to derive it again, you know? I mean, so you're asking me, she's asking me about the last problem in the homework. It's like cosine AX, cosine BX. So what was the identity we worked out yesterday? What was cosine A, cosine B? What was it equal to? 1/2 something. I remember there's a half.
Is it 1 plus, or 1 minus,
It was 1/2 cosine A plus B plus cosine A.
1/2, in parentheses, cosine A plus B plus the cosine of, what was it?
A minus B.
A minus B. Okay. I think that makes sense. So how do you do this problem? Just take this identity, right? And trade this for the integral of 1/2 cosine of what plus cosine of what dx. So we've got what? So basically think about A be AX and B be BX, right? So if I have A plus B, I get, you know, AX plus BX is what? A plus B times X, right? So I've not left myself enough room in here. I guess I'll just write it A plus B, A minus B. Let me expand on that down here. My bad. Integral, I'll pull a half up front, yeah? So 1/2, the integral cosine of parentheses A plus B times X plus the cosine of parentheses A minus B times X. Close square bracket dx. I was about to say, if A is equal to B, we need to think about a separate case, right? If A was equal to B, what happens here? We have the integral cosine AX, cosine BX is what? It would be just cosine squared of AX dx, right? And then that one, we'd have 1/2 of 1 plus cosine of 2AX dx, which would integrate to x over 2, plus 1 over 4a sine of 2ax plus a constant, right? So if a was equal to b, that would be what the case is. But thankfully for you, in problem 360, I said a not equal to b, so you can ignore that, right? So, but you can integrate now, right? Make a u equal a plus bx substitution, make a w equals a minus bx substitution. You need to make a separate u substitution. You need to treat this and that separately, do a different u substitution for each one, right? But I think you guys can finish the problem with that hint. Yeah? Oh man. Other questions? Yeah.
I'm gonna go 337.
337. Let's see what I
I
get.
got to the part of already integrating it. It's just the part where.
Oh no.
What you mean?
No, 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 no. There's no integration.
I mean, I know there's no integration.
Oh. Oh, okay, okay, okay.
I got the thing on thing.
Okay, so like here's an example. ddx of, oh, I don't know, integral of from tangent of x to e to the x squared of, I don't know, 3x plus 7 over x squared plus 200 to the 1000th power. That's ridiculous enough. Let me make those x's t's so it does make sense. dt, yeah. So the way this works is like I've called it FTC3. So FTC2 says the integral from a to b of f of t dt is equal to big F of b minus big F of a, where f prime of x is equal to little f of x, right? So if I think about that with variable bounds, if I differentiate it, I can think about differentiating FTC2, you see? If I differentiate FTC2, so I take ddx of the integral from a of x to b of x of f of t dt, well, that's ddx of f of b minus f of a, where here a and b are functions, yeah? But then I have to do the chain rule. So the chain rule says differentiate the outside function, namely big F prime of b. But then I have to multiply by db dx because b is a function of x. And then I have f prime of a times dA dx because a is a function of x. But big F prime is little f. So that's nothing more than little f of b times db dx minus f of a times dA dx. Now this result is what I lovingly refer to as FTC3. No one else calls it this. I just call it this. And I mean, as far as I know, nobody else calls it that. They just give you homework problems and let you suffer. I present it as a result you can apply. So applying that here, my Bowsers, f of t is this monstrosity, 3t plus 7 divided by t squared plus 200 to the 1000th power. No one wants to integrate that, right? Actually, maybe I could. No, let's not. So I do 3 e to the x squared plus 7 divided by e to the x squared squared. I should have made this stupid thing simpler. Plus 200 to the 1000th power, right? Times what? Times the derivative of e to the x squared, which is what? 2x e to the x squared. And then I subtract this monstrosity with tangent of x in it. So 3 tangent of x plus 7 divided by tangent of x to the squared plus 200, all to the 1000th power downstairs there. And I have to multiply that by the derivative of tangent. The derivative of tangent is secant squared. So times secant squared. And there you go. And so all I'm doing is f of b times db dx minus f of a times dA dx. Take the integrand, evaluate at the upper bound, multiply by the derivative of the upper bound, and then subtract the integrand evaluated at the lower bound times the derivative of the lower bound. This is how to do that problem. 337, right? So that one doesn't look quite as hideous as the one I just made up, but same idea.
I don't know if I'm doing the right setting it up. I don't know if
You should have like natural log of e to the x quantities, like e to the 2x or e to the x parentheses squared plus 3
I have that.
times e to the x.
That's why
And then you have to subtract the natural log of x squared squared, it's like x to the fourth plus 3, times the derivative of x squared, which would be 2x. So,
So that's what to make sure.
uh-huh. You guys have other questions? All right, well, I hope you guys have a good weekend. I'll stop here before I start coughing again.